Okay, welcome back. We're going to continue working on section R.3, the polynomial section. If you're following along in the book with me, I'm going to begin this topic on page 26. So we talked about the exponent rules in the previous video, so I'm starting up on the polynomials here. So first of all, what is a polynomial? We use polynomials all the time in our algebra textbook, so we'll be encountering lots of polynomials, and you probably even haven't thought about them as a term. But what exactly is it? It is a product of a number and variables, various variables raised to whole numbers, whole number powers. So, and it can be the sum of those. I guess I forgot to put that. That's why I was looking at it funny. It's the sum of all of those. So you can have multiple different terms added and subtracted together and making up the polynomials. But what makes it a polynomial specifically is that the exponents on any of your terms have to be raised to whole numbers. So, for example, and it can have any type of coefficient, the number in front of it, but the variables have to be raised to whole numbers. It means it can't be a negative number, it can't be a fraction, imaginary, some other type of number, but a whole number starts with 0 and then counts like just the normal way we would do our counting numbers. 0, 1, 2, 3, and so on. So the exponents have to be whole numbers is the only requirement. And you can have any amount of terms, add and subtract different ones of these, make larger polynomials. So this first example is a monomial. Mono meaning one term, just the one term. We call negative 13 its numerical coefficient, or its lead coefficient. We'll use that term later. But the number in front is the leading coefficient or numerical coefficient. Then the variable is x, exponent 3. Now, this is just a one-termer, so whenever you determine the degree of your polynomial, it's the biggest exponent in the mix of terms. So here we have degree 3. Degree 3. Another example, a trinomial. Here I have 3 terms, and none of these are like terms, by the way. You'd always want to combine any like terms before you made these decisions. So clean it up first if needed. But we have 3 different terms that cannot be combined. So it is a tri, meaning 3, trinomial. Now, to determine the degree of this trinomial, we look at each individual term and say, what is the degree of that term? It has no variable even, so there's a variable would be to the 0 power. So that is degree 0 on that term, just a constant. Here, degree 1, the x is raised to the first power, so that's degree 1. And then the first one, that's the winner, it has the largest exponent, and that is degree 2. So the degree of the whole polynomial is the largest one. Which term had the largest amount of exponents, largest degree, so that's going to be degree 2. Second degree equation. We're going to really work with these a lot in the next chapter. Whenever we solve, it's called a quadratic. X squared, those come up a lot. We factor those and work a lot with polynomials. We graph them, so that's going to be a big deal for us as we progress. But notice what makes it second degree or a quadratic is its biggest exponent is 2. Next example, and this doesn't come up as much in our work as we proceed in the book, but it is worth saying, just to be clear, if you have more than one variable, x squared y to the 4th is on this same one term. There's 1 term, 2 terms, 3 terms. There's 3 terms in this. I already said a constant has a degree of 0 because there's no variable. Here, though, there's 2 different variables, so we have to add the exponents to figure out the degree of that term. It's 1 plus 1 or 2. And then this is going to be our winner for the degree, again, in the front. If it's in order, it should be their first term, but sometimes they mix the terms up. But these have been in order, so the biggest amount of degree is in the front. But the degree of this term would be 2 plus 4, or degree 6. So the first term had a degree 6. So we have a degree 6, 2, and 0. So the overall degree of that polynomial will be degree 6, the largest amount on any one term. So if you're asked to determine the degree, that is how we do it. Then the next thing we'll see in our book on page 27 will be example 5. I'm going to work some example 5 problems with you. We're going to add, subtract, multiply, and divide polynomials in this section. So we start with addition, and This may be someplace you're very comfortable. You've done this a lot in your past, but I'm still going to review it. So when we add and subtract, we just have to have like terms before we can combine. So kind of like they say adding apples and oranges. If you're adding 6 apples and 4 oranges, we don't reduce that in algebra. We just leave it right like that. Those are not like terms. They cannot be combined. But if we have 6 apples and 5 apples, we can combine and say that's 11 apples. So we combine if we have exactly the same variables raised to the same exponents. They have to be exactly the same every way about the terms, but then you can combine the numbers in front. So that's how we handle the add and subtract. So in example 5A part, we're doing an add problem. So really these parentheses don't have anything in front of them to distribute. We could just drop those out, but they are trying to specify here's 2 polynomials. Here's a trinomial plus a trinomial. So combine any like terms. So 2y to the 4th and positive 4y to the 4th combines to be 6y to the 4th. And maybe you want to cancel those out as you do them to keep track. Let's see, y squared can be combined. There's -3, always look in front of it for the sign. -3y squared, 7y squared would combine to be positive 4y squared. That's that. Then for the y's, y to the 1st and a 6y to the 1st combines to make 7y to the 1st. So that's combining like terms. You just have to like everything, like bases and like exponents to combine. And then the same thing goes with subtract. If we were doing a subtract problem like on example B, we would need to distribute our subtract before combining. So notice it says minus all of this parenthesis. So there's really nothing to distribute in front of this first parenthesis. I could just drop out the parentheses there and just bring that trinomial down. And then this negative sign, though, for our subtract distributes. So you do want to distribute a -1, changing each of the signs in the parentheses before combining your like terms. And then just like above, look for anything that's the same. Maybe start at the biggest exponent to get it in a nice order. We're going to have -4m cubed, -3, -1 makes -4. -8m squared, -7m squared will be -15m squared. And then we've got a 4 and a +3 making +7. And then that would be our final answer there. So subtract. And there's some other examples there if you'd like to look at those further, but I'm going to move on to multiplication. So when we multiply polynomials, this is example 6 if you're following along, we're going to use some of those exponent rules that we talked about in the last lecture. So here's an example where we're multiplying 2 trinomials. So those are kind of a pain. We don't really do that all that often, but it does come up. But again, we have 3 terms here times 3 terms here. So it's not the FOIL method if you're thinking FOIL. We do that a lot. But here's just going to be a bunch of multiply. And even when we're using the FOIL method, we're really just distributing. We're saying all 3 of these things are times by all 3 of these things. So you just have to multiply every combination together. How I like to do it is distribute this, 1, 2, 3, distribute it through this parenthesis, then distribute the -4 times each thing, then distribute the 1 times each thing. So distribute it, the 3 things, so all the combinations are times together. So I'm going to start with 3p squared is times p to the 3rd. So when we multiply, if we have like bases, we add the exponents. So that makes p to the 5th. 3p squared times 2p. We multiply the numbers in front if possible. And then p2 times p to the 1st, remember, those adds to be 3p to the 3rd. 3p squared times -8. We multiply the numbers using our multiplication rule, so the signs are different, make it negative. Then I distribute the -4, go through the same process. And you see I'm going to run out of room on your screen there, so I'm going to drop down here. Then I'm going to distribute the 1. There should be 9 combinations once I multiply everything together. Then I combine any like terms. So I'm going to start with the biggest. I see the biggest exponent I have is 3p to the 5th. Kind of put it in a polynomial descending order of the exponent. I have some p to the, I guess just one p to the 4th. Minus 4p to the 4th. Let's mark through those as I address them. P to the 3rds. I do have two of those. I have a 6p cubed and a positive 1p cubed, which makes positive 7p cubed. Then p squared is minus 24p squared, and minus 8 makes minus, is that minus 32p squared. Then go to the p terms, plus 32 and plus 2 makes 34p, and then there's one constant, minus 8. All right, so that's multiplying polynomials. Now what we do the most of in this class and in algebra class is the FOIL method. So this is an extreme example where we've got 3 things times 3 things, and you have lots of combinations just to kind of keep track of. But what we do more of is, like I said, the FOIL method, which we see on example 7. The FOIL method is really just what I did on the last one, double distributing. It says we've got these 2 things times these 2 things, so you've got to get all the combinations multiplied out. So I've got to take 6 times both of these, or 6m times both of these, and then distribute the 1 times both of those. So the way that works out, and let's do it kind of with that thinking, and I'll call it FOIL next. But if I distributed 6m times 4m, that's 24m times m makes m to the 2nd. 6m times minus 3 is minus 18m. Then I distribute the 1. 1 times 4m, and then 1 times minus 3. Then combine my like terms. Usually the middle terms will combine, not always, but in a lot of our examples we do. That happens, and you get a trinomial. So we call this FOIL, the FOIL method, because it comes up so often. But what we're doing when we say F is the first times first. Well, that's what I did anyway, the first times first. Then I did the O, the 2 outer regions. If this were a book and I opened, that would be the 2 outer parts, so 6m times minus 3. Then the I, the 2 inner parts of the book right here, these 2 parts, the 4m. And L is this last term times last term, the minus 3. So I was using the FOIL method, but you don't really even have to consider that. You do it that way anyway from what we learned on the last example. You just need to distribute everything out. The reason why we emphasize this so much, though, is because we're going to be working backwards. On the next section, we take trinomials, and this is one of those most beloved, maybe skills in algebra is to work backwards from what you've FOILed together to try to get it back to its reverse. So it's kind of a puzzle because you've combined some middle terms, and you can't always kind of see how it was before. I mean, of course, we can see it right now looking at that, but if that wasn't up there, could you take this and think about what you needed to FOIL together to get that? So that's coming, and I'm sure you know that. You've seen that in your past. We'll be reviewing that as well. All right, let's try another. Continuing on example 7, I'll do B part. 2x plus 7 times 2x minus 7. So when we do the FOIL method here, the first times first is 4x squared. The outer times outer, because the signs are different, is minus 14x. And the inner times inner is positive 14x. The last times last is minus 49. So this is a special pattern that we use a lot in algebra. It's called the sum and difference of terms, because you've got the sum and the difference of the exact 2 same terms. So if you have that pattern, you might quickly just say, hey, I know this one. I know when I FOIL this, the middle terms have to be opposite. So I always lose the middle terms, and it's just this squared minus that squared. 4x squared minus 49. So again, the sum and difference of the same 2 terms will always multiply to be just the first term squared, the last term squared. How this looks in your green box in your book is, if you have an x plus y times an x minus y, it always multiplies to be x squared minus y squared, what we call the difference of squares. So again, the sum and difference always multiplies to just be 2 terms like that.